For this problem, we need to find the Fourier series coefficients of this signal. It's modeled by this equation, 1 over t times the integral over 1 period of x of t, which is just the signal, times e to the negative j 2 pi n t over big T, all with respect to time. And big T is going to be the period of the signal, which is just when it repeats. So we start with the first pulse at t equals 0, and the next pulse happens at t equals 2. So the period is 2 seconds. Next, we need to determine an interval to integrate over. Well, the interval between 0 and 2 is the easiest one because it gives us one of our bounds is going to be 0. So a sub n is going to be equal to 1/2 times the integral between 0 and 2 of x of t e to the negative j 2 pi n t over 2 dt. But x of t can have 3 different values. So the first value you can have is it can have a value of 1 from t equals 0 to 1/2, or it can have a value of 2 between t equals 1/2 and t equals 1, or it can have a value of 0 between 1 second and 2 seconds. So this gives us 3 separate intervals we need to integrate over, but we don't care about the third interval because x of t will be 0. So it'll be 1/2 times the integral between 0 and 1/2 of x of t, and x of t is going to be 1 between 0 and 1/2. So that'll be times e to the negative j pi n t. Then the next integral is going to be 1/2, and the region will be 1/2 to 1. X of t is going to have a value of 2. And again, it'll be e to the negative j pi n t dt. And the third region will be 1/2 from 1 to 2, where x of t always has a value of 0, so that always cancel out. It'll be a sub n 1/2 times 1 over negative j pi n e to the negative j pi n t between 0 and 1/2. And this next integral, it'll be 1/2 times 1 over negative j pi n times 2 times e to the negative j pi n t from 1/2 to 1. So for this first term here, we can multiply the top and the bottom by j. On the bottom, we'll have j squared, which is negative 1. That'll cancel with a negative on the bottom there. We'll be left with j over 2 pi n. Then we can plug in the bounds to that exponential. It'll be e to the negative j pi n over 2 minus e to the negative j pi n times 0. That'll cancel out. We'll have a 1. And for this next term, this 2 will cancel with that 2. Again, I'll multiply the top and the bottom by j. So the bottom negative sign will also go away. It'll be 1 over pi n, and it'll also plug in to this exponential. It'll be times e to the negative j pi n minus e to the negative j pi n over 2. I forgot the j over there. All right, so over here it'll be j over 2 pi n times e to the negative j pi n over 2 minus 1. We can factor out an e to the negative j pi n over 4, and that'll be multiplied to e to the negative j pi n over 4 minus e to the positive j pi n over 4 times the terms we had before, j over 2 pi n. So from Euler's formula, we know that e to the j theta minus e to the negative j theta is equal to 2j sine theta. However, this e with the negative exponent is positive when it should be negative, so we'll multiply both sides of this equation with negative 1, and we'll get e to the negative j theta minus e to the j theta is equal to negative 2j sine theta. And this is equivalent to what we have there if theta is equal to pi n over 4. So for this first term, it'll be j over 2 pi n e to the negative j pi n over 4 times negative 2j sine of pi n over 4. Next, we can worry about this second term. From here, we can factor out an e to the negative 3j pi n over 4. That'll be multiplied by e to the negative j pi n over 4 minus e to the positive j pi n over 4. And that's going to be all times j over pi n. So these two terms are the same as the two terms we had before. So it'll be plus, and we had j over pi n e to the negative 3j pi n over 4 times negative 2j sine of pi n over 4. This 2 will cancel with that 2. We'll have j times j, which will be negative 1. So that negative will go away. We'll be left with 1 over pi n sine of pi n over 4 times e to the negative j pi n over 4. And for this next term, we'll have j times j, which will be negative 1. So that negative will go away. We'll have plus 2 over pi n times sine of pi n over 4 times e to the negative 3j. I'll actually write it as negative j times 3 pi n over 4. And this is our a sub n equation. Now it's just one more step so that we can rebuild the original signal in Python. We need to find the zeroth harmonic, also called the DC component, and it's modeled by this equation, 1 over t times the integral over 1 period of x of t dt. So it'll be 1 half times the integral from 0 to 1 half, x of t was 1, and then it'll be 1 half from 1 half to 1, x of t was 2, so it's 1 half t from 0 to 1 half plus this 2 will cancel that 2, we'll have t from 1 half to 1, it'll be 1 half times 1 half minus 0 plus 1 minus 1 half. So a naught will be equal to 1/4 plus 1 half, which is 3/4. So a naught is equal to 0.75. Now we can use Python to determine if our coefficient equation is indeed correct. So in Python, I've created a function that uses the equation found in the last step to calculate the coefficient for any given number of harmonic. And I loop through the first 100 harmonics, and I use the Fourier series equation to sum all the cosines and rebuild the original signal. So here's what that looks like. From 0 to 1 half, it has a value of 1, just like it did in the original. From 1 half to 1, it has a value of 2, again, same as the original. And from 1 to 2, it has a value of 0, with a period 2, and it repeats forever. So we have successfully rebuilt the original signal. So thank you for watching.